Have you ever wondered how alternating current gets transformed into the smooth, steady power that energizes most of our electronic devices? Well, a bridge rectifier circuit is often the hero here, and calculating its direct current output primarily involves understanding the peak voltage of the alternating current input and accounting for voltage drops across the diodes. In an ideal scenario, the average direct current output voltage for a full-wave bridge rectifier is approximately 2 times the peak input voltage divided by pi, or about 0.637 times the peak voltage, before filtering. Now, let us dive into why this calculation is so important and what factors truly influence that direct current output. The core principle of a bridge rectifier is to convert alternating current, which constantly changes direction, into pulsating direct current. It achieves this by using for diodes arranged in a bridge configuration, ensuring the current always flows in the same direction through the load. However, that ideal 0.637 times the peak voltage is just a starting point. In reality, each diode in the path of the current flow introduces a small voltage drop. For silicon diodes, this is typically around 0.7 volts per diode. Since current passes through to diodes during each half cycle, you will lose about 1.4 volts from the peak input voltage. This means your actual peak direct current voltage will be the alternating current peak voltage minus 1.4 volts. Another crucial aspect is the ripple voltage. Without a filter capacitor, the direct current output is a series of rectified sine wave humps. A large filter capacitor is usually added in parallel with the load to smooth out these humps, storing charge when the voltage is high and discharging it when the voltage dips. This reduces the ripple, making the output much steadier. The ripple factor, which is the amount of alternating current component remaining in the direct current output, depends on the load resistance, the capacitance value, and the input frequency. A lower ripple factor means a smoother direct current output, which is generally desired for sensitive electronic components. To calculate the actual average direct current output voltage for a filtered bridge rectifier, you start with the peak voltage of the alternating current input. First, determine the peak input voltage, which is the root mean square voltage multiplied by the square root of 2, or approximately 1.414. Then, subtract the combined voltage drop of the two conducting diodes, usually 1.4 volts for silicon diodes. This gives you the actual peak direct current voltage. After this, for a capacitor filtered output, the average direct current voltage is approximately this peak direct current voltage minus half of the peak-to-peak ripple voltage. The peak-to-peak ripple voltage itself can be estimated as the direct current through the load divided by the product of the filter capacitance and 2 times the input frequency. Therefore, you need to know your load current and your capacitor size to get a more precise value. Understanding these nuances helps you appreciate the critical role of components like the filter capacitor and how their selection impacts the quality of your power supply. This also brings us to a key concept called peak inverse voltage, or PIV. This is the maximum voltage that a diode must withstand in the reverse direction when it is not conducting. For a bridge rectifier, the PIV rating of each diode must be at least the peak input alternating current voltage to prevent breakdown and circuit failure, offering a vital safety margin in design. By carefully considering the input alternating current voltage, the diode voltage drops, the filter capacitor's value, and the load requirements, you can accurately predict and design a stable and efficient direct current power supply using a bridge rectifier. This knowledge not only enhances your circuit analysis skills, but also enables you to create more reliable and precise electronic systems for various applications.